Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about the arc length of parametric equations. Okay, so let's take a look. Let's get started. We've worked with arc length before, all right, finding the arc length of a traditional function. So let's see how it applies or can apply to parametric equations. So the arc length L of a rectangular equation is given by the integral from x sub 1 to x sub 2, the square root of 1 plus the derivative of f squared with respect to x. All right? That would be the arc length. Remember, arc length is just a fancy way to say perimeter, right? These mean the same thing. Okay? Basically, arc length is the perimeter of a curve. All right? So if I had a piece of a parabola, let's say, this from 0 to 3, this equation would calculate me the perimeter of that curve, all right, from 0 to 3, okay, if you use it properly. All right, so that's what arc length is all about. Okay, now, the problem is I want to work in parametric form, all right? Well, to work with parametric equations, there is no such thing. Well, f prime of x is not written as f prime of x. So let's come over here. So we're going to say L is the integral from x1 to x2, the square root of 1 plus f prime of x is just another way to write dy dx. So I'm going to write that first here because I think that kind of sets us off in a good direction. Okay, but what is dy dx if I'm in parametric form, right? So dy dx, we've worked with it for a few videos now, is dy dt divided by dx dt, because everything is not written in terms of x anymore. You have both components written in terms of different variables. So in place of dy dx, I should put dy dt divided by dx dt, because I want to do this in terms of in a parametric equation. So we have x1 to x2, the square root of 1 plus, I'm going to replace dy dx with dy dt divided by dx dt squared dx. All right, so now I have a few issues to resolve. The first issue I have to resolve is I got to clean this up a little bit. So I'm going to square each one individually, and I'll come over here to do it, I think. So we have x1 to x2, the square root of 1 plus dy dt squared divided by dx dt squared with respect to x. All right, so now I have this complex fraction, and I want to remove this complex fraction and give myself one fraction to work with in the denominator. So let me go on to the next slide here, and we have right now L is equal to x1 to x2, the square root of 1 plus dy dt squared divided by dx dt squared dx. All right, so I'm going to find a common denominator inside this radical. The common denominator is dx dt squared, right? So let me come over here. Let's do that. The common denominator is going to be dx dt squared, and that means the first term will need a dx dt squared. The second term does not. It already has one in its common denominator. Okay, with respect to x. All right, so far so good. Now, all this fraction is underneath the square root, so I'm allowed to take the square root of each, the numerator and denominator. So I'm going to write that. And we're going to have the square root of dx dt squared plus dy dt squared all over the square root of dx dt squared with respect to x. Now, the square root of dx dt squared, I can do that. The square root of the square is dx dt. So let's write that. And then we'll take stock of what we have and where we still need to go. Dy dt squared over dx dt with respect to x. Okay, now we're almost there. we pretty much eliminated as much as we could from the square root. We obviously cannot take the square root of the numerator, right? These two things are added. You cannot take the square root separately of two terms that have been added together. Okay, so we have to leave this up here. The issue now actually may not be the most obvious one. The biggest issue we have is that dx, because x is the variable of integration. But the problem is this entire integrand is written in terms of t, right? It's not written in terms of x. That's a big problem. So the question is, how are we going to convert this from dt? What we really need this to be is we need it to be a dx. Or I'm sorry, we need it to be a dt, right? We need to get rid of this dx and make it a dt so that the variable of integration matches the variable that's in the integrand. And then we'll be able to convert, obviously, the x bounds to t bounds as well. Okay, so how are we going to do that? Well, what we're going to do is we're going to do exactly the opposite of what we did in the last video. In the last video, we had dt dx in the numerator, and we put it in the denominator as a correction factor. Now I'm going to do just the opposite, and I'm going to multiply the top and the bottom of my integrand by dt dx. Because what happens? The dx's cancel each other out. And I get now an integral. So we'll say t is between a and b, just to give me some letters to work with. So I can replace these x's and put a's and b's in their places. So they knock each other out and leave me with a dt, but that's the variable of integration I want, and it also eliminates the denominator. So I get the square root of dx dt squared plus dy dt squared dt. And that is the equation to represent the arc length of a set of parametric equations. Okay? That's where it comes from. All right, so here's a summary here on the next page. Okay, given a parametric curve C represented by x and y on the interval t between a and b, and the arc length L from t equals a to t equals b is given by the integral from a to b, the square root of dx dt squared plus dy dt squared dt. That's the formula that you're going to use. All right, so we're going to try it once here, just to say we tried it. So L, let's write it down. The arc length is going to be the integral from 0 to 1 here, the square root of dx dt squared plus dy dt squared dt. Okay, so to do this, I need to find dx dt and dy dt. So dx dt is 3t squared. Dy dt is 2t. Then L is the integral from 0 to 1, the square root of 3t squared squared plus, I wrote y, 2t squared dt. Okay, now the most difficult part of these, especially if you're doing them by hand, is the algebra manipulation that has to be done to get yourself in a form that you can actually integrate the thing. All right, so now we're going to square each one of these. That's really all I can do with it. I get 9t to the fourth plus 4t squared dt. So I can't integrate this at all. Certainly can't use substitution. There's nothing I can do with this, but I can factor out t squared, which is actually a really good thing here. So this is the integral from 0 to 1, the square root of. If I factor out t squared, that helps me tremendously. 9t squared plus 4 dt, because now I have two things that are multiplied inside the radical, so I can take the square root of each one. So this is the integral from 0 to 1, the square root of t squared times the square root of 9t squared plus 4 dt. The square root of t squared is t. So this is now the integral from 0 to 1 t, square root of 9t squared plus 4 dt. But now I'm at a huge advantage. That helps me tremendously because now I can use substitution on the 9t plus 4, 9t squared plus 4. Its derivative is 18t. I just need a 1 over 18 for Beach Boys. So this is going to be 1 over 18, the integral, let's change the bounds. If x equals, or t equals 0, u equals 4. If t equals 1, u equals 13. And this is going to be the square root of u du. So that's 1 over 18. Straight line from u equals 4 to u. U equals 13. The integral of square root u, that's u to the half. Its integral is u to the 3/2, 2/3. So that's going to be 1 over 18. Let's substitute the bounds in. We get 2/3 times 13 to the 3/2 minus 2/3 times 4 to the 3/2. And that is the correct answer. You can clean it up a little bit if you want to, but that ultimately is the correct answer. Okay? And that's how you calculate the arc length of a parametric equation. All right, as always, thanks for clicking.